My name is David Rocaforte, and I'm a Senior Application Engineer at MSC Software. Today I'm going to discuss how virtual prototyping can be used to improve the design of latching systems. A latch being broadly defined as any mechanism that locks or prevents motion at one or more degree of freedom between two bodies. Latch applications are seen in products within many industries. The latch can be the weakest link in a design, creating customer dissatisfaction, machine downtime, warranty recalls, and even lawsuits. Common failure modes in latching systems include linkage failure due to misuse or abuse, fatigue loading, inability to mate due to misalignment or unforeseen deflection in the system. In a powered system, there could be a failure to cycle due to unforeseen resistance or reduced power. There could also be failure to trip a sensor or microswitch due to tolerance or deflection in the system. Engineers must design the latching systems to withstand all potential loading scenarios and ensure that the system can operate under all conditions using a finite amount of power. This could be ergonomic limitations for a manual latch or a manual override. In the case of a powered system, one must design within the limits of the hydraulic system or the motor. Therefore, several geometries need to be studied in order to come up with an optimal design that can provide optimal operational performance. Physically testing all these variations is expensive and time-consuming. Simulation helps replace physical prototypes with virtual ones, which can be built faster and studied for a larger range of environmental and loading conditions. This allows engineers the ability to iterate repeatedly, gain more insight into their designs, and improve upon them, while working in their comfortable office. Typically, latches involve large displacements and nonlinearities that make many of these analysis impractical using nonlinear FEA methods. Multi-body dynamics analysis with Adams is the ideal choice for this type of model for accuracy, time of solution, and ease of implementation. Regardless of application or industry, the operating conditions for a latch are similar. Specifically for our simple latch model, the analysis starts with the latch in the closed position. The system is preloaded by some amount due to compression of seals or O-rings. The input to the force controller is an opening velocity. Once the latch is released and the link separates from the striker by a set amount, the desired handle velocity is reversed by an Adams sensor statement and a simulation script. Once the handle contacts the base plate, the simulation is halted with another sensor. Contacts and kinematic constraints are defined, as well as nonlinear seal loads, which are applied to the striker body. Flexible bodies also are incorporated. These improve fidelity and are able to recover deformation and stresses dynamically from the bodies. The handle is driven by a force that uses the PI controller. This applies enough force to attain a constant angular velocity about the latch pivot. This allows us to capture bending and twisting loads in the handle versus driving the joint with the torque or rotational motion. With Adams, we can look at the system in the frequency domain as well as the time domain. Because inertial loads due to vibration can be significant, it is important to understand what frequencies this system is sensitive to in order to avoid excessive loading created by resonances. Subsystem modes of vibration are important, but understanding how they interact at a higher level with the entire system is crucial. Once evaluated in the system model, it becomes apparent that we have some low-frequency content that could be problematic. It is not enough to understand how a nominal design in the perfect world may work. Simulation allows you to explore design space that you would never have the time, let alone money, to evaluate physically. Adams has parameterization and design of experiments capability to aid in running multiple configurations of your design automatically. Here we explore friction properties and misalignment effects on latching forces and capabilities. We can change our static friction, dynamic friction, friction preload, and seal forces to see how they contribute to operating forces. I plotted the difference in actuation force between two runs from an automated design of experiments indicates that a variation in friction and alignment accounted for over 25 Newton delta in actuation loads. This might put a manually operated system over ergonomic limits, or might cause a powered latch system to stall or to not operate. In summary, Adams is the optimal simulation software to help you easily model and assess a latch's complex multi-body dynamics behavior. Incorporating flexible bodies, controls, as well as the ability to look at the frequency domain allows for the necessary fidelity. Finally, leveraging designs of experiments allows you to truly do proper design studies so that you can arrive at the best solution for your application. Thanks for watching. If you'd like to learn more about how Adams can help you solve your latch or other system engineering problems, go to mscsoftware.com.